Now that we've seen that the bijection rule is true for finite sets, we actually proved it, right? We proved that it was true for finite sets. Now we're going to extend this notion of matching as being equal to infinite sets. And now we will make a definition. So it's no mistake that I have written here definition and not theorem, right? It was a theorem when the sets were only finite. Now that we move to infinite sets, this is our definition. We say it is this way. So what I want to get across is that we use our intuition from finite world to place meaning on the infinite world. Okay? Right? Now think about your hands, right? How do you know you have the same number of fingers on each hand? It's because you can match them up in a one-to-one and onto function with a bijection. You can match them up with a bijection. If you can match things up with a bijection, they have the same number of elements. You don't even need to count. And so that's what we're going to do with infinite sets. If we can match them up, then they have the same number of elements. Now notice that everything is exactly the same as the bijection rule. The only thing that's different is we've said sets, not finite sets. This works for all sets. All right, and now some peculiar things happen that you might not expect. All right, so here we have the natural number. We have a function from the natural numbers to the positive integers. Remember that this is the positive integers. And we will see that this function, pretty simple function, f of x equals x plus 1, is both one-to-one and onto. It's a bijection. And so therefore, we will conclude that they have the same number of elements. Now I know you're sitting there saying, oh boy, this guy, he's flipped his lid. He's saying that the natural numbers, right? The natural numbers, let me write them out here. 0, 1, 2, 3, 4. That's our natural numbers. Has the same amount of things in it as the positive integers. Now remember, dot, 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 these go on forever. These are both infinite sets. These are infinite sets. But I know what you're thinking. You're thinking that the integers has one less thing in it than the natural numbers, right? Because the integer starts at 1, whereas the natural numbers start at 0. So it would seem that the natural numbers has one more thing in it than the integers. But see, infinity doesn't work the way that finite things work. Okay, infinity is a lot different beast than the finite world. Okay, and we don't have and we're really using our intuition from finite world to study and understand the infinite. And if you think about it, right, how do we know we have the same number of fingers on each hand? Because we can match them up, right? And so we use that intuition to extend our definition to the infinite world. And look, we can match these up real simply. And because we have infinity at our disposal, right, we're just going on and on and on forever. We're never going to run out of things to match up with. Okay, so now filling out the table, f of x equals x plus 1. So 0 plus 1, that's 1, 2, 3, 4, 5. Let's see. What goes, so let's see, 5, 6 goes to 7. And that just goes on and on and on like that. That totally works. Right? So we ask ourselves now, is this function both one-to-one and onto? Well, let's see. First of all, everything's different here, right? Okay, there's no D and E's. No D and E's. So it's onto. And these are all different, so it's one-to-one. Okay, so it's a bijection. And remember our definition, right? Two sets have the same cardinality if there's a bijection between them. So there's a bijection between those two sets. So that tells us that, in fact, yes, they have the same number of elements.